Okay, maybe we can kick it off. So welcome everyone to our webinar with Edge Impulse and Arduino. So I am Aurélien Lecartier, I lead the solutions team at Edge Impulse, and today I am with Andrea Ricetta, who's working in the Arduino Pro team. And we are going to talk about how to build a glass breaking detector using Edge Impulse and the Arduino Nicla Voice. So first, we're going to go through a series of slides, then going through the demonstration, and we will leave some room for the Q&A at the end. So if you have any questions, feel free to use the Q&A function in the Zoom application. So Andrea, if you want to go.
Okay, great. Thanks, Aurélien, for having me today, and thanks everyone joined this webinar. I'm head of the Pro Customer Success team at Arduino. So basically, we deal with the customer on everyday basis in order to find the right solutions and the right mix of products and projects for their needs. And this also is valid when it comes to ML and AI. So I would like to introduce a little bit the Nicla family boards, where the Nicla Voice is part of, giving some product overview, some application examples, and then I will leave the stage to Aurélien. So let's start with the Nicla family. The Nicla family is a range of industrial grade products with different purposes depending on the sensors that we have on board. But basically, we can identify the family with some key features that are mainly the tiny form factor. All the Nicla has a footprint of 2.2 centimeters, so it's a square. It's a really little board. They can be configured as usual with the Arduino tools in a very easy way. You have instant setup and you can get high-level data depending on the board. So it's easy also to create a wireless sensor network connecting different boards to a single Arduino product or third-party product. So you can build up various scenarios, and then you can move on and expanding depending on the needs. Every Arduino Nicla family board has different sensors depending on the version, but basically they are all industrial grade sensors, and of course can also have on board, so on the edge, low power AI and machine learning, and today we will show you how. And regarding connectivity and deployment, there's a multiple way to interact with the boards, either wireless or wired for nearby communication. That makes fast development way. So thinking about retrofitting something, equipments in a very easy way. So the Nicla family is composed by three different boards. Nicla Vision, that how the name says, it's devoted to vision capabilities. It has also a microphone and a time of flight sensor for measuring distances. On your right hand side, we have the Nikla Sense ME that basically has a pretty huge amount of sensors, starting from sensing. ME stands for motion and environment. That basically covers all the motion sensors, IMU, gyroscope, and then environmental sensor, temperature, humidity, air quality. So there's a really a good amount of sensors. And then we have the Nicla Voice. The Nicla Voice is the queen of today's webinar. So the Nicla Voice, it's based on the NDP 120 from Sentient, that it's a neural decision processor that basically has the role of coordinating all the AI and machine learning that the Nicla Sentient has on Nicla Voice has on the top. And in addition to the microphone that is used, of course, for any kind of sound detection, voice triggering detection. It has also a smart 6-axis motion sensor and magnetometer. When it comes to communication, on the wireless side, the Nicla Voice has Bluetooth Low Energy, and can be used also in a wired way by using standard SLOV connector that basically is I2C, and you can also leverage on the pinout that has it ready out of the box. When it comes to technical specification, I don't want to go in deep and bore you, but basically, as I said, we have the core that it's a Cynthian NDP120 neural decision processor. Then we have a host microcontroller that's Nordic Cortex M4. We talk about the sensors. So thinking about IOs, we have I2C, SPI, ADC. And when it comes to memory, we have 12 kilobytes of flash and 64 kilobytes of SRAM. And we have dedicated SPI flash storage of 16 megabytes for storing data models, whatever is needed, and additionally 48 kilobytes of SRAM dedicated for the Cynthian, for the NDP120. So all in all, this is the technical specification of the Nicla Voice. Now I would like to also highlight the fact that we are partnering with Gimpulse to provide all our users, all our cloud users, to access all the technology that Gimpulse provides. So straight from our cloud, you can access a machine learning tool powered by Gimpulse, and basically within the Arduino cloud, you can have access to the entire Gimpulse Studio without moving out from one system to another. So this is a great opportunity. Here you can do whatever you want, the same that you can do on the Gimpulse Studio. So you can get data acquisition, impulse design, model testing, versioning, everything that also Aurélien will show. This is a great integration also to show how it's easy and seamless deploying a machine learning model within the Arduino ecosystem, because we have a lot of boards that are already supported out of the box from Arduino. The machine learning tool plan is basically available in the maker version for all the included Arduino plans. That is, has 20 minutes per job and 4 gigabytes or 4 hours, depending on the project you are looking for. So 4 gigabytes for storing or 4 hours of audio sampling. While on the enterprise version, we have an add-on dedicated for a cloud for business plan that has 60 minutes per job, or 1000 minutes of total compute time per month that can be exchanged through different boards or different projects. If you want more on this, we have a dedicated page for Arduino, cloud.arduino.cc/plans, where you can see all the differences between the different plans. I would like also to introduce some use case scenarios based on machine learning, based on our boards, especially on the Nikla side. I show you just a few of them, but if you want to go to docs.arduino.cc/tutorials, you can see all of them, and also you can also see how they are made and how to replicate them. So the first one is the connected predictive maintenance tool. So on your, this is a great example of retrofitting. So on your left-hand side, you have a standard industrial machine. In this case, a cartooning machine, but could be anything, any kind of equipment you want to track. And adding what we call the smart sensing, any Nikla board that can track vibrations, can detect noise, or can add vision. Then you can get your data from the machine, send this data to the machine learning tools, create your model, train your model, and then deploy back to the board, and then connect, depending on the version, to the Arduino cloud that where you can create different dashboards, or you can leverage the mobile app to get charts alarms, notification. So this is one of the most used scenarios, I would say, because it's really easy to adapt. It's flexible enough to add one sensing at a time. So today you can use vibration, but tomorrow you can also add noise or detection or vision detection. This is really easy. You can add different Niklas, or you can leverage different sensors that the different Niklas has. One other example is in production line. Component defect detection. This actually come from a customer that were looking for a capping machine. So looking if the cap machine was working well and the caps were tightly firmed or not attached to the bottle. So in this case, he was using the machine vision by detecting this defect, putting the Nicla vision on top of the production line at the end of the production. Then he trained the model based on the images got from the Nicla vision, sent to the Edge Impulse studio, and then deploying back to the board. So this was a really interesting scenario because it enables even with at the POC level, at the prototyping stage, but also during production. And the nice stuff was that the customer was able to iterate during the various stage. So thinking about acquisition, image acquisition, it should be well done. Then image sending to the cloud. So it was really helpful for him to have this kind of flexibility, not only on the hardware side, but also on the software side, and of course on the entire machine learning part. Then this is the glass breaking detection, and this I don't want to spend more words on this because Aurélien will show exactly what you can do with the Nicla Voice featuring the NDP 120. And another use case is a fall detection. So think about elderly people, but think about also people working in remote areas where they are not attended by any kind of means. So there's no way to communicate. There's no cameras in action for detecting people or workers that are working to remote spaces. Then by plugging a Nikla board that detects the movement, so the motion, and you can detect when the people fall from high levels, depending on the board. So you can also detect the height of the worker. So it can be also interesting to know if the worker is falling from high altitudes and and so you can also manage different ways of alerting priorities and send and interacting with the BLE beacons. You can identify which is the area where the worker was working. And so there, inside the fall detection, this is just one examples, but basically the use case can be achieved using the different Nikla boards. When it comes to compatibility, we have different ports. We have all Nikla family sensors that is compatible with Edge Impulse technology. We have also Nano 33 BLE Sense. We have the Portent H7 that it's our other SOM system on module that features dual core microcontroller. So you can see we have a lot of and more will come. Boards that are available and can be used out of the box with Edge Impulse technology. So just a small wrap up regarding Pro. We have plenty of documentation, training, support. We have help center, and of course tutorials and examples you can follow to recreate your projects based on our technology, based on our code, and then adapting. My suggestion is to start your journey when it comes to documentation to pointing out to docs.arduino.cc, and you will find this all sections on the website. So I'm done. So the boring part is done, and I leave the stage to Aurélien. Thanks a lot, and you will say later for the Q&A session.
Thank you, Andrea. I've got a few boring minutes as well because I've got a few slides, but no worries, it's not going to last long. Okay, let me start by sharing my screen. Okay, actually, I need to do it again. Just need to remember to share the audio. Okay, I think we're good. So yeah, just a couple of slides that I was mentioning about Edge Impulse. So like at Edge Impulse, we provide an MLOps platform to basically optimize AI for the edge. So we've got like a full MLOps going from data collection to creating machine learning projects, usually a mix of signal processing and neural network as well, up to the deployment part where you can basically create either directly like a binary, that's basically what we are using with the Arduino Nicla Voice in this demo, or you can also create like an open source C++ library. And one good thing about Edge Impulse is like it's completely royalty free. So if you deploy your model to one device, 100 devices, it's not going to change the pricing. And as I was mentioning, like the inferencing library that we generate, it's like a full open source C++ library that you can reuse in your own application. The other interesting part as well is like we don't have like black box per se. So like I was mentioning, for instance, like signal processing, which is like very important when you want to run machine learning on edge devices. All the signal processing blocks that we have, like around spectral analysis, images, audio, or other type of signal processing, they are also available on GitHub. So you can have like free access to them and look directly at the source code. Just a few numbers about our ecosystem. So we've basically launched the platform a bit more than 3 years ago. If I recall correctly, it was February or March 2020. And so far, we've got more than 70,000 developers on the platform and more than 170,000 projects deployed using Edge Impulse. And part of that, we've got actually like a big chunk of users and projects that are using Arduino. So you can see here the number, we've got like 13,000 plus Arduino developers and 19,000 plus Arduino projects. So when you want to do like machine learning at the edge, you've got like different type of use cases that you can run. You can use like different type of sensors, different type of data. And basically like using the Edge Impulse platform, we cover like different type of use cases that can be like using like simple like accelerometer sensors, audio like we will do today during the demonstration, images if you want to do image classification, or object detection, or even video if you have actually a bit more powerful devices that you have at the edge. But basically, like on this table, you've got a good overview of like what kind of either microcontroller, neural network accelerator, or NPU, GPU that you can use depending on the type of sensors and use case that you have in mind. And yeah, basically like here to close the loops, I was explaining at the beginning that we've got like a full MLOps platform for Edge AI. And as I was mentioning, we do everything from like data collection up to deployment. So for data collection, you can do that in different ways. Like if you have like an existing data set on your computer, you can of course like import this data set in different formats. If it's CSV, JSON, WAV files, if you want to do like audio classification. You can also retrieve data directly from like cloud buckets. So for instance, if you're familiar with like S3 buckets, or Google Cloud buckets. It's something you can basically directly plug into your Edge Impulse project to collect the data. And what's also interesting with active learning is that you can also collect data directly from your edge devices. So either if your devices are connected through a cable, so like in the example I will do today, it's like I'm just using a USB cable, but you could also imagine having an edge device with IoT connectivity or some sort of connectivity, and you can also push like new data to your project to basically like keep improving your machine learning model performances over time. And just before jumping to the demonstrations, just mentioning this new feature we've released that was 2 weeks ago, which is we call like bring your own model. And the idea behind that is we've noticed that we've got like more and more like ML savvy people. So like people are very comfortable using TensorFlow, PyTorch, or any type of machine learning framework, and that are basically like using Python every day in their day-to-day job. And so we've released like this new Python SDK that basically allows you to use any type of machine learning model that you have trained from Keras or other framework, and basically directly profile the model that you have and to check basically the performances of your model depending on the target. So you will get information about the latency, how much flash or RAM it would take on your device. And the other part, which is actually like the one which is also very interesting, is about like directly like creating a C++ library that would get all the inferencing engine to run your model. So if you want more information on that, you can head to basically our website and to our documentation to see how it works. And I will switch to the demonstration. So if you are interested, so you will get also the slides in the next couple of days, but like this project is available publicly. So if you want to copy the link, which is here, so like the mltools.arduino.cc, that's the Arduino instance where this project is running. And that's basically the project 210541. But I can also share it in the chat later on. And I will switch to my project now. So yeah, one thing about the project here that we have, we've used basically like an existing data set, which is called DCA SE, because I didn't want to break like glasses in my apartment. That would be very expensive and not very good for the planet. So we've collected data from this existing data set in order to train our model. And then we will see at the end how we are going to test it using some basically some YouTube video with glass breaking sounds. So when you want to start with your Edge Impulse project, so like my project here is already created, but usually like you're going to start from scratch. So either you start by adding new data, which like as I was mentioning like earlier, you can either add like existing data from cloud buckets or directly from your computer. You can also like collect data directly from devices. And if you look at this upload your model, that's the BYOM features I was just mentioning a few minutes ago. So different ways to get started. And if you don't really have like a use case in mind, you can also start directly like with a tutorial. So we've got like different tutorials available for like gesture recognition, to perform like object detection, and also like audio classification on keywords. So if I go step by step in the project, so as I was saying, like we've collected data from this DCA SE dataset. And as you can see, like the data collected in total is not that much. It's around 7 minutes. But it's usually like enough for this kind of project when we want to detect glass breaking sounds. So we can see like in details that for the training data set that I have, I've got like 300 samples. And for the test data set, I've got like 54. And then I can just filter out easily between the different labels. So I've got here like the glass break labels. I can select each of them and listen to the samples. And there are also like additional features, like because in this one, basically like each sample is 1 second, but sometimes you want to collect data, like big WAV files. So if you want to split or crop your audio files, you can do that directly within the UI. So when you click here on the 3 dot, you've got like other features to do like crop sample or split the sample. So that would basically like allow you to select exactly the portion of your audio file that you want to add in this category. And then the next part, this is where it gets interesting. This is about like creating what we call the impulse. So like the impulse, it's something I was talking about like at the beginning of the presentation. That's usually like a mix of signal processing and neural networks. You want to do classification. So like especially with audio projects, you could go directly from like your raw audio file to a neural network, but when you look at some like audio waveform, you usually got like more meaningful features if you look at the frequency domain compared to the time domain. So that's why we usually do like a chunk of like signal processing before running into the classification. So for some of you who are like familiar with signal processing, it usually like involves like fast Fourier transform in order to go from the time domain to the frequency domain. But you will see that through the user interface, even if you're not familiar with signal processing or even with machine learning, you can just go through the whole process without modifying the different parameters. So like in this example, like, oops, sorry for that. In this example, we've got basically defined like a window size of like 968 milliseconds. So that's basically coming from a requirement of the sentient NDP accelerator that's sitting on the Arduino Nicla Voice board. So we set this window size to 968 milliseconds. And then we add a sentient audio signal processing block. So if I show you here, basically we've got also different type of audio processing blocks that we could use in this project. But because like the sentient NDP accelerator got like a fixed like hardware DSP on the chip, we basically need to reproduce their DSP processing within the platform. So that's why we select this audio sentient for the project. But if you want to look more into the details, we've got all the blocks, as I was mentioning, are available on GitHub, and you can look at the documentation to see how it works in details. But basically, like the sentient block is very similar to what we call like MFE. So if some of you are familiar with audio extraction, that's sentient and the MFE block are quite similar. So like if you look at the spectrogram of both, they would look quite the same. So we use the audio sentient for signal processing, and then we just run through a regular classification. So we can also do like some regression, use some transfer learning that would be useful if we want to do some like keyword spotting. And we could also add some like anomaly detection block if we want to do some specific anomaly detection on either audio or different type of signals. So going to the next step here, if we look more in details about the sentient block. So as I was saying, like you don't need to modify the parameters if you're not familiar with signal processing. I would say that 95% of projects will work really well with the default parameters. But if you're interested in changing the different parameters, you can do that from here. And once you've saved your parameters, you can then generate the features that will basically be used as the input feature that would go into the neural network. And so once you generate the features, we have this like dimension reduction technique we use to be able to display like the different samples here on this view. So like you can see in this example, in orange, we've got all the different like background noise samples, and in blue, that's all the glass breaking samples that have been collected. And so it's interesting to get this view because you can, like, even here looking at the clustering, you can see we've got like different clusters between the glass breaking one and the non-glass breaking sound. So like in orange and the blue, you see we've got like kind of good clusters. There are some of them that are a bit closer to the noise samples, but overall that's pretty good. It looks quite well. So just looking at that, we know that the neural network will be able to do some decent job to classify the different classes we have. And then, so like the next step here is about defining the neural network model. So in this particular example, because we've selected the sentient signal processing block, the neural network is like automatically populated with default architectures that have been tested on with the sentient NDP chip. So you can use either like a dense network, which is the one showing here, or you can also use like a 2D convolutional neural network if it's something that would work better for you. By experience, the 2D convolutional would work better if you do some keyword spotting. But here in this case, it's like glass breaking sound, so it's like different from keywords. So in this case, it's better to stay with the dense network. And so here we've got like a very simple UI to modify like the number of training cycles, also like modify directly the neural network architecture. So you can do that directly using the graphical interface. So you can add extra layers, modify the number of kernels, for instance, and such. And if you are very familiar with like Keras and TensorFlow, you can also directly write the code in Python. So like here I can switch to the expert mode, and from there you can go directly to the Python code and define manually your own network. And so once you've defined everything, you can just click on Start Training, and you will get like the training performances showing on the right side. So here you can see for this project, we've got like 89% accuracy, which is quite decent, like based on the number of samples that we have. I think if I remember well, we've got a bit less than 2 minutes in the training data set for the glass breaking sound itself. So that's quite good performance. Of course, like if you want to do like, if you want to build like some production level project, in this case, you would need like much more, a bigger quantity of data for that. So here, that's basically like all you need to do in order to create your impulse, including like signal processing and then machine learning. As I was saying, it's even if you don't know anything about signal processing or machine learning, using like the default parameters would work well for 95% of cases. One other feature that actually is even more interesting if you're not too familiar with machine learning is the Eon tuner. So like the Eon tuner, that's basically our auto ML feature. And the way it works is it will look for both the best signal processing and neural network parameters to basically like optimize the performance of your model. And so you can have like different criteria to optimize your model. So it can be like the latency. For some use cases, you want to be sure that when you run the model on the target, it can run under, let's say, like 100 milliseconds. For other use cases, what's more important is how much space it would take in memory. So you can also like optimize the model based on that. So depending on your specific needs, and especially like depending on your target, it's something you can configure and use the Eon tuner to find the best model that would fit your requirements. So far we've been through the whole training of the model. And if you've looked like at the beginning when I was looking at the data set in data acquisition, so if I go back there quickly, actually, you see here in my training set, I've got like 300 samples, and in my test set, I've got like 54. So it's usually like a good idea to be able like to test your model like on a different data set than the one you've used for training. So this is what we can do here from model testing. And so I thought I run it before, but apparently no. So I'm going to run it again here. And so what it is doing here is like it's taking all the different samples from my test set, and it is going through the signal processing block, and then through the neural network block to run the classification. And then it will give me basically like the accuracy for each of the samples and the overall accuracy for my model. And you see actually here my model is performing really well, even better on my test set compared to the training set. I just got two samples that are highlighted in red here that have been like incorrectly classified by the model. And if you want to know a bit more about for instance, this particular sample, you can go to show classification to get a bit more details about what happens. So it will basically like create a window and gives you like the percentage for each class for this particular one. So you see for this one, like the glass breaking got like a 38% accuracy, which is not good. And then we can basically look as well at the waveform of the sample. And so yeah, like if I listen to this sample, I mean it seems like glass breaking, but it's actually really, really short. So if it's something we would want to consider to like improve our model, probably we would need to collect more data with such type of signal. So that was the model testing, and finally the last part here is about the deployment. So here, because we've selected like the sentient DSP block, it's in the deployment section. It's only showing the libraries and firmwares available for this particular project. But yeah, if you look at our website and documentation, we have support for like lots of different boards and libraries. In this particular example, so we can either build the sentient NDP library, which is like specific to the NDP chip that's sitting on the Arduino Nicla Voice, or to actually go faster, you can directly build like a binary firmware. So you click on you select the firmware for the Arduino Nicla Voice, and then you start building. And so it will compile the whole firmware on the Edge Import Studio. And at the end, you will get like a zip file with the binary plus some like flashing scripts specific to your operating system. So for all the different targets we support on the platform, we've got like flashing scripts for Windows operating system, Mac OS, and Linux. And so like here, this build could take a bit of time. So we may not wait until the end. But maybe one last thing here about this posterior parameters that you can see. So this posterior parameter is something so specific to sentient, where basically the goal is like optimize the performances based on force acceptance rate and force reject rate. But this particular one works really well for keyword spotting because it's using some calibration data sets that are basically like people talking. So it's like really well suited for keyword spotting. Here for our project, it's something a bit different. So we don't go through this specific posterior parameter search. So we just use this no calibration data set in order to use like default parameters for our project. And so basically, if you are interested in what it's doing, here you can look at this particular JSON posterior parameters. And so you will have like the different classes in the project that we want to detect. So in this case, we only have like the glass breaking. And from there, you can tune some parameters to optimize the performances on the target. So here you've got, for instance, like a threshold. So in this example, like if we have, if we detect some glass breaking event and we've got like 70% accuracy or more, we would trigger basically the interrupt to say, oh, we've detected some glass break. There's also like a windowing that you can tune and other parameters. And all of this information is also on the Edge Impulse documentation. But yeah, basically like all default parameters is something that would work out of the box. So you can see like the model is still building on the on the right side. But I've already got the model flashed on my Nikla. So I've got my Nikla here, and I will connect it to my computer using the USB cable. So if you see well, you see this green light, it's basically saying it's like loading the model on the chip. So this one takes a couple of seconds. And once it's not green anymore, which is the case now, we can basically like start the model. And so here, because I've built a firmware using the Edge Impulse Studio, so like building like the binary firmware, it's coming with some like AT commands interface that you can interact with using the Edge Impulse CLI. So like here in my terminal, I can run this Edge Impulse run impulse command. And it's basically now interacting directly with the board. And it's running the inferencing and waiting to see if we are detecting glass break or not. And so as I was saying at the beginning, like the way I will simulate the glass break will be to play some YouTube video. I'll try to keep that on the same window. And I will also disconnect my headphones. Just reduce my speaker, otherwise I may kill all of your ears. Okay, so if everything went well, you should have heard the glass breaking coming from the video. And you see here in my terminal, we got the matches from the glass breaking interrupts. And yeah, so I think that's it for the demo. Any questions you have? We've got 10 to 15 minutes left for the presentation. So thank you, everyone.
That was really great, Aurélien. I think that we have some questions in the chat.
Yeah, I've opened the Q&A as well.
The Q&A. I can take the first one. So can we use GSM modules directly in the Nicla Voice? Just like the Uno is connected to other Arduino boards such as the Uno. It depends on the GSM module. Could be, yeah, because we have different kind of signals available on the pinout. So it really depends on the module.
Okay, thank you, Andrea. I will do the next one. Is the machine learning prediction process on the cloud side or onboard processing for this example application? So yeah, it's a good question. So we do all the training is done in the cloud on the platform, like I was showing in the demonstration. But like the inferencing, so like the machine learning prediction is done directly on the device. So you don't need to get like an internet connection to get the prediction. It's all done locally on the target.
I can take the next one. That Juan ask, interesting device. What is the power consumption for the Nikla? If I'm not wrong, it's with the stock firmware. So what we send to the customers with a pre-trained model on it. We are around 0.80 millis, while when the model is running 0.4 idle and 0.8 when the model is running. This is more or less with the stock firmware.
Okay, thank you. So okay, that was this one. Does Edge Impulse Cloud uses GPU instances to do model training? So by default, we use CPU instances, but for enterprise customers, it's something we can also enable. So like, especially like if you do like image classification or object detection on big data sets, yeah, you will see like a big difference regarding like training time. So with we can set up like GPU instances, but that would be only for like enterprise plans. Oh, and that was another question. Where do we find your Python code or simple processing to model training pipeline? So it's on our GitHub, and if you look at Edge Impulse on GitHub, we have a repo called processing blocks, and you will be able to find the code from there.
I lost. Okay. How do you combine data from both Nicla Voice and Nicla Vision to use both camera and audio stream to detect and classify the events of interest? Is this possible? Well, it's absolutely possible using two different projects. As we are working with different boards, you can do it with different projects, and then having all the boards communicating together. Or if I'm not wrong, Aurélien, you can also mix up the different signals right from the Edge Impulse study, right?
So we do some sensor fusion, but having like one only one model to do image classification and audio is not something we can do. But usually what users would do is to have like two models in parallel and then run the correlation directly on the target.
Yeah, exactly. Or on two boards, different boards. So
Yeah.
one of the stuff is that at runtime you can choose also the model that you want to run. That's another interesting stuff. So yeah, there's a multiple way of doing that. This is for us. It's challenging to find a supplier that sells the battery, that it's compatible battery for Nicla Vision. Yes, you can write to our support at arduino.cc. We are working to get some batteries out from our stores. Unfortunately, it's quite challenging for all the documentation and everything connected to sending batteries, at least lithium batteries, lipo batteries. So we are working on this. But if you want to write to our support, we should have some answer for that.
All right. Do we have from Peter? Approximate distance that the microphone can hear in the field. It's not something I've tested. I don't know if it's something we have in the data sheet, but that's a near field microphone from
Yes.
what I think.
Yeah, I don't have the exact answer, but thinking about it's a near field, I would assume something like in the range of meters, but
Yeah.
not.
Do you know if we could plug like a different microphone using the GPIO on the Nikla, or is
Yes,
it?
we have dedicated for that, a dedicated connector for external microphone. So in that case, it could be another option.
Okay, sounds good. And another one from Peter. Did I see a model of or setting that allows the sound be tracked as it moves? We don't have settings for that. I'm thinking if it's something that can be done easily, but it's usually something you can do with like an array of microphones, like the way it's done usually in signal processing. But yeah, it's interesting. Maybe it's something that could be done with. I'm thinking if it could be done with just machine learning, but I think it's really hard if you only have like one microphone to do it. I think you would need at least two.
Yeah, because it depends on the level recorded from each microphone. Then you can determine some way the angle of arrival or something like that. Yeah.
Yeah. Okay. It's good. We've got lots of questions. It's like I'm closing the question, but there are new ones opening. What about the algorithm? How can we customize the algorithm when the event is happening and do some things? Yeah, good question. So like I was showing and how to use like the binary firmware, which is like a quick way to deploy the model. But the firmware is also available on GitHub. So that's like the easiest way if you want to, if basically you want to tune the firmware itself. So if I was thinking, if you go to our documentation, like docs.edgeimpulse.com, you've got a dedicated page for the Arduino Nicla Voice, and you have a link as well to for the firmware. Or you just go on GitHub, Edge Impulse GitHub, look for Nicla Voice, and you will find a repo for this one. And from there, you can just basically go to the Arduino sketch and add your own command there. All right.
Okay.
Does this webinar have Nicla Voice giveaway?
Not from my side, unfortunately. I don't know on your side. No, we don't have giveaway. But probably we can think for the next, right?
Yeah.
That's a good.
Can we just inference on Nicla Voice without calling the inference function? That's something you can do that. Like, how would you run inferencing without calling it? I mean, you will always need like a inferencing model from that's like Cynthian compatible to run it. So for this one, yeah, you will need the compile library. But I think by default the Nicla Voice comes with some Alexa model, right?
Yeah,
it's
correct.
flashed with one model. Yeah. Okay. I noticed during testing, Nikla, the audio should be loud enough for the sound to be detected. So probably it's similar to the other question we had about the microphone, the type of microphone. I will double check. I'm not sure if there's a way to tune the gain, but maybe there is some parameter to tune the audio gain on the mic.
That's a good question. I need to check. Yeah, usually yes, but I'm not sure right now. But basically, by the way, everything is open source. So in the repo, you can find all the documentation and directly the code for checking it. But that's a good question.
Yeah.
Is the Nicla Voice compatible with the Maker GSM 1400? Theoretically, yes, depends on the use case. But again, we have GPIOs ready that you can use for communicating between the boards. So depends on what you need. If you need to exchange data, no. But probably if you have your model running on the Nicla and you want to send something over cellular, you can through the GPIOs connect the two boards and then decide the logic.
Okay, we've got 2 minutes left. Let's see. Here's a power consumption for audio detection, the same for keyword detection. Yes, that would be the same. So like the NDP chip that's sitting on the Nicla Voice, it's like a very low power inferencing chip, and it's actually running continuously. So it doesn't matter if it's to do keyword spotting or the type of audio detection. But of course, you could also like decide to turn it off for like 5 minutes and maybe just run the inferencing every couple of minutes, depending on your use case. But for this particular question, that will not make a difference. Maybe let's look at the last one. I think that was similar distance from sound.
Yeah.
Lots of question about the microphone. Can we download the train TF flight model from Edge Impulse? So you can do that from, you can download like the TensorFlow model from your dashboard, which is here. So it's something you can do, but like for this particular project, just remember we use like a Cynthian signal processing block that like specific to their chip. So it would also need to match what has been done in signal processing. But yeah, from any project you've developed on Edge Impulse, you can download the TF Lite or the Keras or TensorFlow model.
Okay, I think that we are of the hour. Wow.
Yeah, thank you everyone for all the questions. I think we will have a look at the remaining questions, and we can send a follow-up email in the next couple of days, so you can get a link for the presentation, and probably the video will be put on YouTube in the next weeks, and so you'll get the link as well.
Great.
Thank you everyone.
Thanks everyone.
Have a good day.
Bye-bye.